So let us come to the ultimate class of this transport phenomena. Today is the last class of this course for the present semester, and in today's class we will discuss something fundamental ideas about the Hesler diagram, and after that we will solve some numerical problems related with the fins, with the Laplace equation, and one or two numericals from the unsteady state heat transfer. The concept of Hesler chart is very important so far as your experiment cooling of ingot in the transport phenomena lab is concerned. As you know that this chart is of immense industrial and practical importance to determine the temperature at a particular point in the case of an infinite plate, in the case of an infinite cylinder, and the other shapes, with the condition that the x by L that should be equal to 0. That means x is a particular location where temperature is to be determined, and L is the characteristic dimension, or L or delta you can say, as I have taught you in the previous classes, that the A delta V, that is called the dimensionless position. In that quantity A delta V, that delta stands for the characteristic dimension. So when and where you have to determine the center line temperature in the cases where lumped heat capacity analysis cannot be utilized, that means Biot number is not much lesser than 0.1. In that case, the Hesler chart can be used to determine the temperature in an infinite plate or in an infinite cylinder under unsteady state heat conduction. So prior to go for the numerical problems, it would be essential for ourselves to go into some of the fundamental aspects of this Hesler chart. So basically this Hesler chart it is basically a temperature time plot. It is basically a temperature time plot with involvement of four dimensionless numbers, as number A, the first dimensionless number which is involved is dimensionless temperature. This is defined as T minus Tf divided by Ti minus Tf, where Tf is the temperature of the fluid. While discussing the case of the unsteady state heat flow in a solid body having finite internal resistance, I have used Ta instead of Tf. So far as the temperature of the fluid or temperature of the ambient air is concerned, there are so many notations which can be used at places to places. So Tf is the temperature of fluid, and this TF is many times it is represented as TA, many times it is represented as T infinity, all have the same meaning. Second dimensionless number which is involved in this Hesler chart is the dimensionless time. Dimensionless time. This is also called Fourier number. It is defined as alpha t upon L square, where L is the characteristic dimension here. It is defined as time elapsed. It can be defined as t divided by L square by alpha. So it is, if you evaluate the dimension of this quantity L square by alpha, you will find that this has a dimension of time. So this ratio is defined as time elapsed divided by time taken by the body to attain the steady state condition. That means what is the time that has been consumed in order to heat up the material to a stage so that the steady state condition can prevail. So this is called the dimensionless time. The third quantity which is involved here in this Hesler chart is the dimensionless position. Dimensionless position. This is denoted by letter G. G is equal to 1 for infinite plate, G is equal to 2 for semi-infinite cylinder, and G is equal to 3 for spherical objects. So third is the dimensionless position, and the fourth one is the dimensionless heat transfer coefficient. Dimensionless heat transfer coefficient. This dimensionless heat transfer coefficient, this is also known as Biot number NBI, that is equal to HL upon K. Okay. Another important thing which is related with the Fourier diagram, related with the Hesler diagram is this. The question may be brought in you people's mind that under which circumstances this Hesler chart can be utilized. This Hesler chart can be utilized. So this chart is utilized when Fourier number is greater than 0.2. This is most important thing. Please remember it, that the Fourier number must be greater than 0.2 if anybody wishes to apply this Hesler chart. Another point is this curve is plotted. This curve is plotted between T minus Tf divided by Ti minus Tf and Fourier number for different 1 by Biot number value and G values. This curve or chart is valid for Biot number between 0 to infinity and larger Fourier numbers. The chart is used to determine the center line temperature. The chart is used for evaluating the center line temperature for which XYL equal to 0. The third important point is, if anybody wishes to determine at a position which is not fulfilling this condition x by L equal to 0, what necessary step needs to be taken in that case? So, the next point is regarding that. So, the third important point is, in order to determine temperature with different x by L values, correction factor needs to be used. Such correction factors can be evaluated from the companion Hesler diagram. The next point is 0 less than 1 by Biot number less than infinity. From here it can be determined 0 less than 1 by Biot number infinity. The first line on this chart corresponds to 1 by Biot number equal to 0. So, if I am saying that the Biot number is 1 by Biot number is equal to 0, it means K divided by HL, that is equal to 0. That means K by HL is equal to 0. It means H is infinity. That means the convective heat transfer coefficient on the surface of the body is infinite. What does it mean? It means the internal resistance, it means the body has a zero surface resistance. That means there is no resistance to heat flow so far as the surface is concerned. That means the body has a zero surface resistance. This is all about the Hesler diagram. You will see. I would like to request you to arrive at the Hesler diagram, especially for the infinite plate. The diagram is of such type. Along the y-axis, there is the dimensionless temperature is plotted. Along the x-axis, the Fourier number is plotted, and At the various 1 by Biot number value, the curve straight lines are there. How this chart can be utilized, I will solve a numerical problem later in the class to have a flavor of this chart. My request from all of you is, please go through the Hesler diagram, try to visualize or try to conceptualize this Hesler diagram, what basically it is, and how this chart can be utilized in order to solve unsteady state heat transfer problem in the cases where the Biot number is greater than 0.1. So let us try to solve some of the numerical problems on the theoretical portion that we have gone through in the recent classes. The first representative numerical problem is from the heat transfer through the fin. So, question is, the temperature distribution in a long rod may be given at theta equal to theta 0 e to the power minus mx. One end of the rod is inserted into a furnace and other is projected in the air, that is the ambient air. Okay. After the steady state is reached, temperature of the rod measured at 2 points, temperatures of the rod measured at 2 points ten centimeters apart are found to be 125 degrees centigrade and 91 degrees centigrade respectively. Calculate the thermal conductivity of rod. Calculate the thermal conductivity of the rod if temperature of the ambient air is 28 degrees centigrade, dia of rod 2 centimeter, convective heat transfer coefficient 15 watt per meter square Kelvin. So let us try to proceed for the numerical. This is basically the principle of Ingenhousz method of determination of thermal conductivity of materials. The method that I have given the name in the first or second class of the transport phenomena, while we are discussing the importances of the empirical correlationship for the determination of thermal conductivity, that why these empirical correlationships are required for an engineer, only due to the fact that the determination of thermal conductivity through the experimental technique is quite a cumbersome technique. It will take a lot of time. A practicing engineer may not have such an ample time to determine the thermal conductivity of the material on the shop floor every time by utilizing the experimental pathways. So, let us proceed in this numerical problem. So, as the temperature distribution is given, the theta is equal to theta 0 e to the power minus mx. So, or we can write theta x is equal to theta 0 e to the power minus mx and theta x plus delta x, because 2 points I have to consider, that is equal to theta 0 e to the power minus m x plus delta x. So, theta x divided by theta x plus delta x, that is equal to e to the power m delta x. Now, let it be question number 1. Now, theta x, that is equal to how much? Temperature at a particular point minus temperature of the ambient air, that is 125 minus Tf 28, that is equal to 97 degrees centigrade. Similarly, at another point distant 10 centimeter apart, that is theta x plus delta x, that is equal to, at that point the temperature is 91, so 91 minus 28, that is equal to 63 degrees centigrade. So, putting here, so 97 by 63, that will be equal to e to the power m into value of delta x is equal to 10 centimeters apart, that means in MKS unit, that is 0.1. So, m into 0.1. So, from where you will evaluate the value through calculator, it will value comes as 4.316. Now, refer to the principle of the pin. While solving the differential equation for rectangular pin or in any type of pin, we can refer that the m square is equal to ph, that means the periphery circumference into the convective heat transfer coefficient into k into the cross sectional area through heat flow is taking place. So, 4.316 whole square, that should be equal to P, because the rod is cylindrical in nature. So, this is equal to pi into d into h divided by k into cross sectional area will be circular. So, pi d square divided by 4, so 4 will come here. So, pi d cancel, that is equal to 4h upon k into d, or the value of k is equal to 4 into h. What is the value of h given here? 15 divided by 4.316 whole square into diameter. Diameter, what is diameter is given? Two centimeters. So, 2 centimeter, it will be converted into meter, that is 0.202 meter. So, that will be equal to, when you calculate it, it will come as 161 watt per meter Kelvin. This is your answer. My request to all of you that I am solving one or two representative examples only. You should go through all sort of the possible numerical problems related with each and every topic of the transport phenomena. Let us try to go through one example of this Laplace equation and its solution through finite difference approximation. Consider the following mesh. To evaluate the temperatures for the nodes 1, 2, 3 and 4. The diagram is given as per this figure. This is your diagram. This side has a temperature 100 degrees centigrade. This side has a temperature 100 degrees centigrade. This side has a temperature 100 degrees centigrade. This side has a temperature 500 degrees centigrade. The nodes are, let us suppose this is the node number 1, this is the node number 2, this is the node number 3 and this is the node number 4. We have to evaluate the temperature T1, T2, T3 and T4. So answer is using this finite difference approximation, the linear equations for the nodes can be given as, for the node Mn, let us suppose representative, can be given as that T m plus 1 n plus T m minus 1 n plus T m n plus 1 plus T m n plus 1 plus T m n minus 1 minus 4 T m n, that is equal to 0. This is the representative equation on the basis of finite difference approximation that we have gone through in the previous classes. So considering the node number 1, node 1, right? So equation can be written as T m plus 1 n, that means this node, that means for node 1 the equation can be given as T2 plus T m minus 1 n, this side, that means 100 degrees centigrade, plus T m n plus 1 T m n plus 1, it means (500 centigrade) plus T m n minus 1, that means node 3, that means T3 minus 4T1 equal to 0. Similarly, for node 2, the equation can be given as, I am writing the equation directly. So 100 plus T1 plus 500 plus T4 minus 42 is equal to 0. Let it be question number 1, let it be question number 2. Similarly for node 3, T4 plus 100 plus T1 plus 100 minus 43 is equal to 0. Let it be question number 3. And finally for node 4, the equation can be given as 100 plus T3 plus 100 plus T2 minus 4 T4, that is equal to 0. So there are 4 linear equations. And 4 variables are there. You can evaluate through the numerical method and the answer will arrive at T1 is equal to 250 degrees centigrade, T2 is equal to 250 degrees centigrade, T3 is equal to 150 degrees centigrade, and T4 is equal to 150 degrees centigrade. So this is the methodology, because if you further solve these equations, then it will arrive at T2 plus T3 minus 4T1 plus 600 is equal to 0. Okay. T1 plus T4 minus 4 T2 plus 600 is equal to 0. T1 plus T4 minus 4 T3 plus 200 is equal to 0. T2 plus T3 minus 4 T1 plus 200 is equal to 0. When we solve this equation, we will get the result as T1 is equal to 250, that is equal to T2 is equal to 250, and T3, T4 is equal to 150 degrees centigrade each. Now let us come to the one numerical problem related with the lumped heat capacity analysis. Question number 3 is a copper plate of 2 mm thickness is heated up to 400 degrees centigrade, is heated up to 400 degrees centigrade and then quenched into water, at 20 degrees centigrade. Find the time required for the plate to reach the temperature of 40 degrees centigrade. To reach the temperature of 40 degrees centigrade, assume the convective heat transfer coefficient is assume H equal to 80 watt per meter square Kelvin. Plate dimension is equal to 30 centimeter into 30 centimeter. Specific heat capacity of copper at constant pressure, that is equal to 0.4 kilojoule per kilogram Kelvin, and density of copper rho Cu 8800 kilogram per meter cube. If you calculate the Biot number in this case, it will arrive at a value much lesser than 0.1. So, the lumped heat capacity analysis, this lumped heat capacity analysis is also in many books it is referred as Newtonian heating or cooling. So, if in the examination it has been asked that what is the Newtonian cooling, then it means the heat transfer case where this lumped heat capacity analysis can be made applicable. Such type of cooling or heating is what is known as Newtonian heating or Newtonian cooling. So, using this lumped heat capacity analysis, T minus Ta divided by Ti minus Ta, that is equal to exponential minus Ha divided by rho Cpv into T, or in order to make it positive, let us suppose Ti minus Ta divided by T minus Ta, that should be equal to exponential Ha divided by rho Cpv into T. Now, Ti minus Ta, now Ti minus Ta, that is equal to 400 into water temperature is 20, so this is equal to 380, and T minus Ta that is equal to the temperature which is required, that is 40 minus 20, that is equal to 20. So, also we have to determine the A. So, if a plate is there, let us suppose this is the plate that you have and you are subjected to quenching. So, this entire plate will be dipped in the quenching bath. That means the area which is being exposed to the quenching fluid is the area from the both sides, from this side and as well as this side. So, area will be 2 into 0.3 meter into 0.3 meter, that is equal to 0.18 meter square. And what about this volume? If you calculate the volume, then this area needs to be divided by 2, because area into thickness. So, area into thickness, so that is equal to that is equal to 0.9 into 2 mm, 2 by 1000 mm is equal to 1 meter. So, it will arrive as 1.8 into 0.18 divided by 2, 0.09, sorry, 0.09 it will be. So 0.09 into 2 by 1000, so that will be equal to 1 by 8 or 1.8 into 10 raised to the power minus 4 meter cube. So putting here, let it be equation number 1. Hence from equation number 1, 380 by 20, that should be equal to exponential h value 80 into area 0.1 meter square into T divided by rho, that is 8800 into Cp. This is given in the 0.4 kilojoule. It needs to be derived, it needs to be expressed in terms of joule only. So that needs to be multiplied by 1000. So it will come as 400 into the volume, that is the 1.8, or you can write 0.18 divided by 1000, right? That can be given as exponential. When you solve this quantity, it will arrive at 0.0227 t. Taking the log on both sides, so ln 19, that is equal to this much, 0.0227 into t. So the t value will be, so the t value is equal to ln 19 divided by 0.0227, and it will come as 129 seconds. This is the time required by the plate to reach at the temperature of 40 degrees centigrade. If it has been heated up to the 400 degrees centigrade, it has been quenched into a liquid with a temperature 20 degrees centigrade. The last problem is related with the Hesler diagram. So let us come to the problem number 4, and this is the last problem, and this is the last portion of the class of your transport phenomena. So the question 4 is that a steel plate of 20 mm thickness and 1 meter square surface area is quenched from a temperature of 800 degrees centigrade to 100 degrees centigrade in water at 30 degrees centigrade. Calculate the time required to obtain the midpoint temperature. It means the Hesler diagram is to be used to obtain the midpoint temperature of 400 degrees centigrade. The given quantities are H, that is the convective heat transfer coefficient, is equal to 60 watt per meter square Kelvin. K is equal to 30 watt per meter per Kelvin. You can also write a watt meter raised to the minus 2, K raised to the minus 1 here. And the alpha, that is the diffusivity, thermal diffusivity, is 0.023 meter square per hour. Okay. So let us proceed in this numerical problem. So thickness of the 20 mm, that means the 2L value is given as per the previous class. So semi thickness is equal to 20 by 2 mm, that is equal to 10 mm, that is equal to 0.01 meter. Okay. Ti 800 degrees centigrade, because the T in the Kelvin scale, as I have mentioned earlier, so that will be equal to 1073 Kelvin. Tf, that is the temperature of fluid, is equal to 30 degrees centigrade, that is equal to 303 Kelvin. Midpoint temperature is equal to 400 degrees centigrade, that is equal to 673 Kelvin. So what is the value of the dimensionless temperature difference? That will be equal to 673 minus 303 divided by initial temperature of 1073 minus 303, that is equal to 0.48. Also, and 1 by Biot number is equal to K upon HL. What is the value of K upon HL in this case? That is 30 divided by 60 into L is the 0.01. That is equal to 50. That is equal to 50. Now referring to the diagram, this diagram, this is for the infinite plate. This is for infinite plate. Please keep this Hesler chart in front of you. Even if in the examination, if the Hesler chart is not provided, then the relevant data required for that numerical problem to solve will be given in the question. So corresponding to T minus Tf divided by Ti minus Tf value is equal to 0.48, and 1 by Biot number is equal to 50. You will get the corresponding Fourier number is equal to, from the chart, that is equal to 37. Now you have arrived at the Fourier number is equal to 37. So because of the fact that this is a dimensionless time, the Fourier number is basically a dimensionless time. So from this Fourier number, once the Fourier number is being known, so the time required to attain that temperature during the quenching phenomena can be determined accordingly. So if Fourier number is 37, that means alpha T by L square is equal to 37. So T is equal to 37 into L square by alpha, that is equal to 37 into L, that is the 0.01 meter whole square divided by alpha value is there. Alpha value is there 0.023, but this is in terms of the meter square per hour. So meter square per second, you have to convert it into meter square per second. So you have to divide with this 3600. So ultimately it will be equal to 37 into 3600 into 0.01 whole square divided by 0.023, and this will come as 579.13 seconds. So this is the time that will be required by that particular plate during the process of heat treatment. So dear students, this completes your course on the transport phenomena. It is my utmost request to all of you to go through the numerical problem as much as you can. Anytime if you are facing any difficulty in order to solve any of the numerical problems, or if you have any doubt, you should feel free to contact me on my contact number that has been given on the WhatsApp or the calling number. So more and more numerical problem you will solve. It will be easier for you people to appear in the Viva Voce examination for the end semester examination as well as the lab examination. So in both the examinations you have to face the Viva Voce, that will be through the mobile contact. So it is my utmost request to all of you that please go through all the aspects that have been dealt during this transport phenomena course, and as and when required you may contact me on through the phone call or through WhatsApp. You can easily contact me. So best of luck for the examination and for your future. Thank you.